Today I will talk about I2C programming, and we will send data from we are going to read data from the slab device JS1307 and send all those data in the ST line, and then we can receive by the master device on CORTEX M4 processor, and we will we are going to read data from this RAM memory location. This is false address in the RAM memory. Okay, by giving only the first locations and the address of the slab device, that is JS1307, it will begin to read continuously from all those address. And as the brush says, we only need to give the device address and the first locations, and inside it can be the address location can be continuously increased by the I2C. So we will just write the code here. This is including the library of Java microcontroller on CORTEX and CORTEX. And we will define the slab address. Here, this is 0x6807 for the JS1307. Okay. And here we will write the function I2C initialization. And here I will explain this function later. Okay. And here we will write another function for I2C1 reading from the slab device memory. And so we will pass the slab address and memory address, and then this is the first memory location address. That means that 0x 00. And background means number of data we are going to read. And we will pass the data up to the pointer. And I will explain this function little later. Okay? Because if I explain this separately, then it will not be in the flow. So it will be jumbled up. So for example, so in the main function, this is the main function. So we will do stack and empty array. An empty array consisting of 7 values. Here I would like to call the I2C initialization function in this line, but I haven't write the function yet, so let me write the function and then call in this line. Okay. So let me write the function. Here we will error. And okay, suppose we are going to receive data from the slave device, and suppose if there is sometime in some exceptional case or rare case we want to receive data from particular slave device, but there was no data at all we found here at the time of trying to receive data from the particular device. So in that case, so the byte count will be 0, so we are not receiving any data. So we will see the byte count less than or equal to 0. That means there is no data at all. Then return -1. Stop again further executions. Okay. So this is I did not I am coming to that this is not I2C initialization functions. This is another that I'm thinking about that I2C sending read and reading the data from the slave device. So let me write the I2C initialization function. So sorry, my bad. System control will use PIO and equal to JX01. So in I2C initialization functions, the system control is using this register or CGC GPIO, and we are putting the value JX01. So this RCGC GPIO says supply a clock source to any of the bit 0 to 7 of this RCGC GPIO and choose a particular port. So I'm putting value 01. 0 means this, and 1 means this. So in this bit 0, I'm supplying the clock source. So I'm choosing port A or GPIO A, and then in the next line, system control is using RCGC I2C and as for the value 0x02. Now the system control is using RCGC I2C register, and this RCGC I2C register, the 32-bit register, is saying supply a clock source to any of the bit 0 to 3 and to choose a particular I2C modules. So I2C modules can be I2C version 1, I2C version 2, I2C version 3. So this is the register, and this register says supply clock source to any of this. As we are putting the value 0x02 here in the code 0x02, so 0x02 in hexadecimal is 0010. So we are writing 0010. As I'm writing 1 here, I set this bit. So I'm choosing I2C version 1. You can choose any of the I2C version 0 to 3, 1 to 3. This is version 0, 1, 2, 3. I'm choosing I2C version 1 to use in my code. Here I've chosen GPIO A. So I will say GPIO A implies AFS in out. Then we'll develop this okay C is 110000. So this GPIOE 14 is using AFSL register, and this AFSL register says you choose a particular bit you want, and then method set for whatever functions you prefer, either for I2C or you are SPI, timer, whatever. This dual pins can be used now for many options. And then another is and this is same. This one FF means F means 1, so FF means 1 1, and this is negations of 1 1 is 2. So I'm planning this 2 bit 6 and 7 of the port control register because I want to put other value. So in the next line I will say in the next line, in the bits 6 and 7, I'm putting the value 33 of this port control register. This is same again. Here I'm clearing in this port control register, I'm clearing the bits 6 and 7, and here in the same port control register, I'm putting the value 33 in the bits 6 and 7. Because putting this value 3 in the bits bit 7 make the bit 7 of this GPIOE port A, this bit 7 set only for I2C ST, and putting the value 3 in the bit 6 of this port control register will make the bit 6 of this GPIOA, that is this one, set only for I2C ST1. Now this bit can be used of the GPIOA 6 and 7 bit can be used only for I2C1. Is 1 0 0 and 0 is this. So C is this and this GPIOA port A is now using this then register, and it says whatever pin you have chosen. Here I'm choosing only 2 pins. Whatever bit you have chosen, set it for as digital so that it can be used for any digital, because everything we are doing here is in digital, as we are not using any analog. And then I is 1 0 0 0 2 2 2. So this one I'm setting the bit 8. Sorry, the bit 7 to follow the open drain circuit system. That means this is open run. That means this is the 7-bit. This 7-bit is I2C is only meant for I2C SG serials data, where all is it. In I2C, sometimes the master, some master is allowed to share the bus. So sometimes some master may be having output circuit of low level function transistor connected to it, and some master having the output circuit connected to low level function transistor. And because of that, the high output level circuit and low level output circuit sometimes current may pass. So because of that, the short circuit happens from one device to another device, having a high level output circuit, and current flow, it passes from that to another device having low level output circuit. Then short circuit happen, and that is not good. Short circuit means something lost in this going to be lost in the circuit, so that is not good. So what ODR system follow is it maintain the device to have only operate with device having output circuit connected to low level transistor, so that there is smooth functionings and not any kind of short circuit. So this is only saying there is smooth functionings and not any kind of there is not any kind of short circuit, and that's all. Not any kind of short circuit in the connection. And then now we will choose the master. Sorry about that. How to say one implies MCR. MCR is a register, and when it's set, it is on the bit 4. It choose it enable a device to operate as a master. Master function is enabled, so a device now will work as a master. So the device or the slab device, sorry, the CORTEX M processor here will now begin to work as a master. That means it will generate the clock for the whole system of transmissions. So that's it. This one is I2C MCR register, and when this bit 4 is enabled, master function is enabled, so the device is in master mode. That means master mode means it will generate the clock for the whole system of transmission. And then I2C one implies MTPR. Putting the MTPR equal to 7 makes the data transmit at a speed of 100 kilobit per second. So that's all for I2C initialization functions. We have choose a particular port. We have choose I2C version 1 here. We have queried this 2-bit. We have said this 2-bit for can be used for many functions options using this register, And register bit 6 and 7 of this register is clear, so that we can put the value 33 in the same register BCTL, so that the bit 6 and 7 of this GPIO is set only for I2C SCLs and I2C SCLs and I2C SGA only. And this one is making the pin whatever we choose here, 6 and 7, we choose only 6 and 7 here so far, make it digitals. And OTR means connect the pin 7 specific only for I2C SGA to follow the open drain system, so that there is smooth functioning in the circuit and not any kind of short circuit. And then setting the bit 4 of the MCR register here to choose our own CORTEX and processor as a master, so that it generates the clock for the whole system of transmission until it is complete, until the data transmission is complete. And this one is making the MTPR value 7, so that the speed of data transmission is 100 kilobit per second. This is all about I2C initializations. And let's write the code of data reading from the select device. So I will write char I2C1 and I will pass select address. I will pass memory address. I will pass in byte count. This is select address again, and this one is first memory location in the RAM location of select address. From here we are going to read the data, and this one is how many data we are going to receive from the select device, byte count, counting the data, number of data. And this one is data. This one indicates that we are going to use the data pointer to get the data. We will take a variable called error, and this is just a variable, and then sometimes we want to receive data from the select device, but in sometime we find there is no data we can receive. So at that time the byte count will be 0 as no data is going to receive. So in that case we will say if byte count less than or equal to 0, that means there is no data to receive. So if byte count less than or equal to 0, return -1. Stop execution. -1 means stop execution. But if there is data that we can receive from the select device, then we will choose that select device first. So we will store the address of the select device first in the MSA register. So we will say I2C1 imply is using MSA register and set the value to store the slab address in the MSA register left share 1. What does it mean is that, okay, here the slab address we use is 0x68, so 6 is 110. Let me explain again. And 8 is 1000. The slab address we are using here is 6 and 8 is 1000. Okay, so this is the slab address value, this one. So slab address is a 7-bit address. This is 7-bit only, not 8-bit, and it is used to store from the bit 1 to 7 of the MSA register. And so it is, this is the MSA register, and it is 7-bit only, that address, slab address, and it is used to store from the bit 1 to 7 of this MSA register. The bit 0 is not used for storing the address. This bit 0 is used for other functions like detecting whether we are receiving from the slab device or whether we are transmitting to the slab device. So we will store that slab address only from the bit 1 to 7. This is bit 1 to 7, and so let's put the bit 0. Okay, this is bit 0 and this is bit 1 to 7. So we are shifting to the left one side and then store the slab address from bit 1 to 7. Okay, we're shifting to the left one times and store the slab address from bit 1 to 7. So we're shifting to the left one times and store the slab address from bit 1 to 7. Okay, that is the meaning. And then here I will write I2C implies. I'm also going to send in the brace right, it says send the slab address and then first memory location address, that is ROM of the slab address, so that we can make it read from there continuously. So I'm going to send the first memory address, the RAM inside the RAM memory inside the slab device. So let's put it in the MTR register. MTR register is a 32-bit register and is used to store the data that we are going to send during the I2C transmission process from the bit 0 to 8, from 0 to 7, and this memory address is going to be 0x00 because this memory address will be we are going to read from this memory address. This is RAM memory address starting from 0x00 inside the RAM memory. This is the first locations in RAM memory, and it has address 0x00 and it is a size of only 1 byte. Okay, this is the slab device GS1307. So okay, that address, this address is this address, right? First RAM memory address. Inside RAM memory of the select device. And this is the address is also a data array. So address is also a data, and so we will store this data in the MDR register, and we will send in the bus, okay, in the select device from the master. And so this is that MDR register. This is MDR register where we used to store the data to be transmitted during the transmission from the 0 to 7. Okay, that's all. And just we are storing in that MDR register to be transmitted in the I2C data bus. And since we are having this select address and then memory address, we will start the transmission and then do the transmission. Okay, so I will use, now I will say I2C is using MCS register, and its value equal to 3 because 3 is 0011, and here we are going to send the select address. That means we are transmitting the select address. That means we are writing the select address. Okay, so we will use MCS as write control register. This one MCS is now using as write control register, as we are going to transmit the data. We are transmitting the data, that means we are writing the data. So okay, we will use the bit run and start to start the transmission. Okay, so we will use this 2-bit only. Okay, run and start, that means 11 means 3 in hexadecimal, okay, in decimal, and 11 is hexadecimal 0011. Okay, so that's why I'm writing the value 3. And so the transmission will start as I have said the start bit here. So in the next line the transmission will be surely start. So let's write here, this is just the variable we take here. Okay, just let's write, I will explain it. So here transmission is starting, and let me explain these functions. So as in this line, in this particular bit, it says the start bit is set. So in the next line transmission, we will write the transmission is starting. So this is the same functions. So let me write here, the transmission is starting means the bus is busy in sending the data. So we will write here while the bus is busy as the transmission is started. So we will write here, well, the bus is busy. So I2C is now using MCS register, and its value is equivalent to 1. 1 means the busy bit. So it is saying I2C is now using MCS register, and its value is equivalent to 1. 1 is the busy bit, so I2C is again busy. Okay, here the bus is busy. Okay, I2C is busy means the bus is busy in transmitting, and the bus is busy. We know, okay, the bus is busy. That means that is the status of the bus. Okay, we know the status of the bus after reading, okay, the status of the bus, and so we are reading. So I2C, okay, cannot is now doing, okay, reading. So because of that, we will use I2C as read-only control MCS as read-only control register. Okay, this MCS as read-only control register, and we are using the bit 0 because the bus is now, okay, busy in transmitting all those address. So we are using MCS as read-only control register and use the busy bit to express the bus is busy. Okay, so the bus is busy, and when the bus is busy in transmitting all those address, this address, we want to check if the address so far is acknowledged by the select device. That means acknowledged means ready to receive any kind of data, whatever so far going to send by the master in the I2C bus, it will be received by, we want to check if it will be received by the select device. So here in the I2C data transmissions, when the address is sent, we check the acknowledgement, okay, bit, whether the select device want to, okay, receive the data so far, whatever going to send by the master. So here we are sending the address, so we will check only the address acknowledgement bit. So we will write in the code here, return to check the address acknowledgement bit. Return I2C is now using the MCS register and is now equivalent to 0xE, and it means 111 here. So now it is saying, okay, I2C is now using MCS register, and MCS register value is equivalent to 0x0E, and E means 111. So while the bus is busy means it is reading the status of the bus, so it is using the read-only control register, and we will like to check when the bus is busy. We will like to check if there is any error or, okay, not, and that will be, okay, that will be known by, okay, reading, okay, the bus, what the bus is, okay, inside the bus, if there is any error or not, we are reading, okay, in the status of the bus, if there is any error or not, we are reading. So we will, okay, use MCS as read-only control register here, and we will read if there is any error or not through this bit. Okay, and here we are sending the address, so we will check the address acknowledgement bit. If address is acknowledged, then there will be no error. This error will be 0. If address is not acknowledged, then this error will be 1. Okay, if address is not acknowledged, this value will also be 1. Okay, your data is not, okay, we are not sending data, so we are not considering again this bit here. Okay, we are not checking. Okay, so I will write here. So I will check only this 2 bit here. So the first is this one is data acknowledgement, as I'm not sending data. I will not check that, so its value will be 0. And the next is address acknowledgement bit. If address is acknowledged, then the value will be 0, so I will write here 0. And if address is acknowledged, then there will be no 0 and there will be no error, so its value will be 0. So I will write here the busy bit we are not considering because we are checking only the error. Okay, we are checking if there is error or not, and error is usually caused by this 2 bit address acknowledgement bit or data acknowledgement bit. Okay, is either caused by address acknowledgement bit or data acknowledgement bit. So we're not checking busy bit here, so busy bit value will be 0. So if there is no error in sending the address, then this value will return. If there is error in sending the address in the I2C transmission bus, then the data acknowledgement bit will be 0. This data acknowledgement bit will be 0 because we are not sending data. We are sending only the address. So if address acknowledgement bit is not acknowledged, then this bit value will be 1 because address is not acknowledged. That means the receiving device doesn't want to receive any more data that is going to send by the master. So the receiving device doesn't want to receive the data going to be sent by the master in the I2C bus. Okay, so if the address acknowledgement bit is not acknowledged, then the value will be 1 for it. Since address acknowledgement bit is not acknowledged, error will be 1. And here we are not considering the busy bit as we are checking only the error, so busy bit will be 0. So if there is any error in sending the address in the I2C bus, then this error value will return. So here that is the functions. So the bus will be busy in transmitting the address, and we are checking if the address acknowledgement bit is acknowledged or not by checking all those the 3 that is data acknowledgement bit, address acknowledgement bit, error, and we are not considering busy bit here. Here I'm also checking writing the data acknowledgement bit. I'm also writing the data acknowledgement bit, not here. Sorry. Yeah, here. We are writing E means data acknowledgement bit, address acknowledgement bit, and then error. So that one. So what I'm talking? Yeah. So here the bus is busy transmitting those address, and we are checking if there is any error or the address so far sent is acknowledged or not. And like that, if there is error, then this value will be sent. If there is no error, then this value will be sent. Okay, return means send. Okay, and if there is error, then it will be stored here. If there is no error, then that 0000, that will be also stored here. And so because of that, and so the bus here we are transmitting and checking the error. If there is error, then we will write if error, then return error, and the transmission will be over. Okay, transmission will be stopped. And suppose address is acknowledged, and so we have choose so transmission of this is successful. That means sending the slab address successfully means we have choose a particular slab device to be used in our transmission. Then we want to read from that slab device here. Here we are sending the slab address, so we are writing the slab address, transmitting the slab address in the I2C bus to choose a particular slab device, and we want to read from that slab device. So we will change the from writing to reading. Writing means sending. Reading means receiving. Because we want to read from the slab device. So how we will change is how we will change the mode is from writing mode to reading mode is let's write simple instructions. Just take it easy and just write the simple instruction. What I'm writing here is, I will explain here. It's a simple thing. Here we are writing the slab address in the bit 1 to 7, because slab address, as we know, that it is only 7 bit, and this bit is not used for storing the slab address, but this bit is to detect whether the state, whether we are transmitting to the slab device or we are receiving from the slab device. So putting the value of this bit 1 means we are receiving from the slab device, and putting the value 0 in this bit means we are transmitting to the slab device. So in the first right conditions, when we are sending the slab address in the I2C bus, we put this value 0. That means we are transmitting to the slab device. To choose that particular slab device, that means we are transmitting the slab address in the I2C bus. So slab address, this one is a slab address, and here I have to write that RS, the 0 bit values, RS values, RS bit values plus 0. But I don't want to, I can also not write this plus 0, because it has no meaning. I mean, it has its meaning, but we can also just omit it. But here, so that means plus 0 means I am writing, that means we are transmitting to the that slab device to choose that particular slab device by sending this address in the I2C bus. We just want to omit this because we can also not write it. Plus 0 is, we can also just omit it, right? But plus 1 is we cannot omit it because in mathematical calculation or any kind of calculation, it has certain work to perform, so we cannot just omit it. The overall result will be something else that we doesn't want. So because of that, here we don't omit and we write plus 1, and plus 1 and 1 is the value of that RS bit, this RS bit, and RS bit values 1 says we are receiving from the slab device, and this is just slab address from the bit. It is 1 to 7. From the bit 1 to 7 only, that slab address, so we are shifting 1 to the 1 times, we are shifting to the left 1 times only, so that it is stored from the bit 1 to 7. That means this is the slab address 68, and we are storing from the bit 1 to 7 by shifting to the left 1 times. That is the expression, shifting to the left 1 time and storing the address from bit 1 to 7. And this is the RS value 1, indicating we are receiving from the slab device. When RS value is 1, it says we are receiving from the slab device. So we are changing the mode from writing mode, transmitting mode, to receiving mode. That means reading mode. In the I2C bus. And then then now we are going to read from the slab device. And sometime we see that there is only one data we can read from the slab device, or there is more data we can read from the slab device. So we will write I2C1 is using NCS register, and this value equal to 7. 7 means 111 in hexadecimal. 0 we can just omit. So 7 means 111 in hexadecimal. 7 means 011 in hexadecimal, but we are considering only this particular, right? So here 1 is run bit, and this one is dot bit, and this one is stop bit. And so we are going to receive data from this slab device. So here this one is we are going to receive from the slab device, so we will use MCS as write only control register, because we are going to write data from the slab device to the master by sending the data in the I2C bus. So we are we are going to write that data from the slab device to the I2C to the master device memory. First in the buffer, and then from buffer to the memory. And and that's the way. So we are using MCS as write only control register. Okay, and then we will use, how we will use this MCS as write only control register is by using its respective bit, right? So we will use the bit we want. So we will use the bit 0 run. Run means execute whatever command necessary. Okay, and then start means we will start the transmissions, and we will stop the transmission after sending the byte, because here is only one byte we are considering. So we will say stop the transmission after sending that byte. Okay, so that's the meaning of that. I2C is now using MCS register and use value equivalent to 7, and 7 means actually use that run bit and then start the transmission, start bit, and then stop the transmission after sending that byte, because we are considering only one byte here. Oh, I didn't write sorry. So 1 byte. Okay, so this is the condition when only 1 byte is there. So I will write byte count equal to 1. When byte count equal to 1, that's the condition, right? I2C1 is using MCS register and is using the MCS register value is equivalent to 7. What actually 7 mean is the run bit, start bit, and then the stop bit. It means run whatever command necessary, start the conditions of start the transmissions, and then stop the transmission after sending that byte. We are considering only 1 byte here. So else if there is more byte, not only 1 byte, then the conditions will be I2C1 now is using MCS register and the value equal to 0x0p. 0x 0 that b. We can write 0x0b is equivalent to 0xb. So I will write only this. And the value of b is 1011 in hexadecimal. So I2C is now using MCS register and its value is equivalent to b. What does it actually mean is this bit, b. So this one is run bit, this one is start bit, and this one is the acknowledgement bit. This one, run bit, start bit, and then acknowledgement bit. Here we cannot use stop because we are sending more than 1 byte. So we cannot say stop the conditions, stop the transmissions like that. Here we are saying we are setting the stop bit because it is the only 1 byte, that means the last byte. So stop the transmission after sending this last byte. But here we are sending more than 1 byte, so we will not say we will not use the stop bit, because stop bit says stop the transmission after sending this byte. And also I would like to say something here. This one is considering the only one byte, that means the last byte. So we don't need to send the acknowledgement bit, this acknowledgement bit, because sending not the acknowledgement bit indicate the transmission is over. The transmission is over, and so the receiving device, the slave device will know that this is the only one byte the master device is reading from the slave device, and after that the transmission will be over. So we will not send the acknowledgement bit, that means acknowledgement bit is not sending, that means negative in acknowledge, that means acknowledgement bit is not sending. So it's saying transmission is over, and so the slave device will know the transmission is over and no more byte to send. And transmission is over, that's all, transmission over. And here there are more data to send, so the acknowledgement bit is set, because after receiving is byte by the master, the acknowledgement bit is checked because of that. And here stop is cannot be used because we are we are going to read more data from the slave device by the master. The stop says transmit that data, that only one data, and then stop the transmission, as we are sending more data, so we will not set the stop bit. So that's the conditions of sending one byte, the last byte, and more byte. So we have set the condition, then we will send the data. We will send the data from the slave device to the I2C bus. So we will say error equal to I2C1 web 2 done. This one is the bus is busy, and we are checking if the data acknowledgement bit is acknowledged or not, and that is the conditions here. That is the functions. I2C is now using MCS register value is equivalent to 1. 1 is the busy bit, so the bus is busy, I2C bus is busy in transmitting those data. And then we're checking while transmitting the data in the bus, if the address and the data acknowledgement bit is acknowledged or not. If not, then error, and error is usually caused by acknowledgement bit or data acknowledgement bit. So we will write error is usually caused by address acknowledgement bit or data acknowledgement bit. So we will check if there is error in sending the transmission. That means this data acknowledgement bit is acknowledged or not. If acknowledged, then it will be received. All those data that we send from the slave device to the I2C bus will be received by the master. If not acknowledged, then will not be received by the master. So because of that, we are checking this 3 bit in 2 tails. That means 1110 means E. So here I'm writing E. Okay, so let's check. Okay, so if data is acknowledged, then data acknowledgement bit, this one will be 0 if data is acknowledged. Okay, data so far sent is going to be received by the master. Then data is acknowledged by pulling the SDA line loop. So its value will be 0. And then here we will address acknowledgement bit is not check here because we are not sending the address, so its value will be 0. And since the acknowledgement bit is acknowledged, then error will be 0. And here the busy bit is not considered here because we are checking only the error. Okay, so its value will be 0. So if data is acknowledged, that means the master wants to receive the data soever sent by the select device in the I2C bus, then there is no error, so this value will be sent, return. If data is not acknowledged, then data acknowledgement bit will be 1 since data is not acknowledged, and this address acknowledgement bit we are not checking here as we are not sending address, so its value will be 0. And then the error will be here data is not acknowledged, we are considering here, so error will be 1. And then the busy bit, we are not considering checking the busy bit here as we are checking only the error, so the busy bit value will be 0. So if there is any error in transmitting the data, then this value will return. Okay, if there is no error, then this value will return. Okay. So if there is any error, it will be stored here. If there is no error, then 0000 will be stored here. So we will write if any error, if error, then return error and then stop the transmission. Okay. But we have to store the data right, so we will just store the data whatever we save, and there, because I2C is now using MTR, and because MTR register is the register where whatever we receive from the select device is used to store in the I2C operations, data transmission operation, whatever we receive from the after receiving from the I2C bus, whatever data is to store here. So we will put that data in this data pointer. This is actually the first index of that array. This one. Again, this is array of 7 index, 7 values, but its value are all 0, 0, and the first index is null. And that first index is now that data we get here, it will be stored here. Mai hình hiện thì xin lỗi bên And then after this, okay, we have stored the data, and then here, okay, we are sending, okay, 1 byte, and also the condition of, this is the condition of sending, okay, 1 byte, and this is the condition of sending, okay, more than 1 byte. So we are, okay, considering both the condition, sending of 1 byte, sending of more, okay, byte. So if there is sending of 1 byte, then the transmission has to be over, right? So let's write, okay, if byte count equal to 0, that means no more, okay, byte, okay, left. That means after sending, okay, after receiving the byte, okay, no more, okay, byte left, byte count equal to 0. Then we will say close the transmissions, complete the transmission. So we will write here, well, I2C1 is using MCS register and 0x forger. So I will explain, okay. This one is 4, this one is 0. That means this is the 6th bit. Okay, the 6th bit is a bus busy bit, and when this bit is low, the transmission is complete. Okay, the transmission is complete. This is the 6th bit of this MCS, okay, and read control as read control register. Okay, and here we are checking, okay, here the bus is busy in still now, okay, the condition is the bus is busy and the bus will be, in sending the last byte or, okay, more byte, and then, okay, here we are considering, okay, the case of sending, okay, the last byte. The last byte, we want to say, okay, finish the transmission. So we will, okay, use, okay, I2C now using MCS, but MCS register and this value equivalent to 0x for 0. That means use, okay, the bus busy bit, okay, in order to complete the transmissions. So when this bit is using, that means it will be, okay, 1 after some time, so the transmission is complete. Okay, and then since the transmission is complete, successfully return 0, that means no error. Okay, that's it. And in the next line we will say if there is many byte, if there is conditions, if there is, okay, many byte, okay, here it is saying, okay, the conditions of if there is 1 byte or, okay, more than 1 byte. Okay, and here we will say, okay, if there is many byte, if the condition is many byte, then do you know, okay, what I'm saying? we are focusing here if there is only one byte. Okay, else maybe there may be more than one byte. Okay, but here we will say if there is many bytes. If there is many bytes, more than one byte. Okay. Let me explain again. Don't mind. Okay. Here we are saying if there is only one byte, else maybe more byte, but focusing on if there is one byte. Here we are saying if there is more than one byte, because we are saying greater than one, that is more than one byte. Then let's write I2C1 MCS register equal to 9. 9 means here I2C1 is now using MCS register and its value is equivalent to 9. So 9 means 9 means 100. Okay, so this one is run bit and this one is acknowledgement bit. That means the condition is execute the run command. That means execute whatever the command necessary, and we are writing here we want to check the acknowledgement bit, because here we are going to send many data right from the slave to the master. So we want to acknowledge whether that data will be wanted to received by the master or not. The acknowledgement bit only says that will the master says a master will pull down the SDA line and indicating acknowledge that it wants to receive the data that is going to be sent by the slave device in the I2C bus. The master will receive. So we want to check the acknowledgement bit because of that. And because of that we are writing here only this run bit and then the acknowledgement bit, as we are sending more data. And see, I'm not setting this start bit here. I'm not choosing the start bit to start the transmissions, because I have already started the transmissions in the before line of code. Here I have already started the transmissions. I need to set the transmission start bit here, and also I need to set the start bit here. Because this is else condition. Else is or. If this line is working, then this line will not work. If this line is not working, then this line has to work. So in either case, I set the start bit and then start the transmission process. So I don't need to start the transmission process again, as it is already start from before. So I'm not setting the start bit here. So this is the conditions of setting in the how to transmit the byte, many byte, run, and then the command necessary and then acknowledge whether the data is wanted to be received by the master. I'm not setting the start bit because it's already start the transmission from before. So here I'm only going to send in the hardware it's already set. I mean, in the hardware you might be thinking but that is if that is not the options, if byte count is not 1 then we are going to come in this byte count greater than 1. But in that byte count equal to 1 but in the hardware the start bit is set, right? So because of that we don't need to set the start bit in the hardware again, as this is all about hardware code, right? So because of that, and here as we have set the condition for sending many byte, we will send those byte. So this is I2C 1 when till done. In the hardware we have to also think about the setting in the hardware also besides writing all this code that will act as software, and because we are actually writing the software to send all of those hardware. So we are sending all those data here. Not we are sending only one data at one time, and then we will write a load to send all those data. Here I will write, instead of if, I will write while so that I can send all those byte. So here the bus is busy, that means data is sending, but it is sending only 1 byte at one time. So here it is sending only 1 byte. And here the bus is busy, that is 1 byte is sending. And then here I'm checking if that 1 byte so far sent is acknowledged or not. So if the data that byte we are sending is acknowledged, then want to receive by the master, acknowledge means then that data bit will be 0. We are not checking address bit here, so it will be 0. Then error bit will be 0 because data is acknowledged, data bit is acknowledged. We are not checking BC bit because we are not considering BC bit here, as we are checking only the error. So this will be returned if the data so far sent is acknowledged by the master by pulling the STA line low. And if the data so far sent, the data so sent, that 1 byte so sent is doesn't want to acknowledge by the master, then data acknowledgement bit will be 1, and we are not considering address bit here because we are not sending address here. Then this error will be 1 as data acknowledgement bit is not acknowledged, and BC bit will be 0 as we are not considering BC bit, as we are only checking the error, if there is error or not. So here that 1 byte is sent, the bus is busy, sorry, this is the condition. So here 1 byte is sent, and then checking again that byte will be acknowledged by the master or not. And then After this we will write if in sending that byte, if there is error, then error will be written here. So we will write if error, then return error, and transmission is over. And then we will write here byte count minus. As we have done one transmission of data here, so the byte count will reduce because there are one byte already sent, so the byte count reduced by 1. So the byte count will be from 7 to 6, as we are going to receive 7 data in total. The byte count will be now 6. As we are so here is 7 index in total, so 7 index, that means 7 value is there in this empty array, and that means we are going to receive 7 data. So that is the byte count. So we are counting so byte count will be 7, as we are going to receive 7 data. So here 1 data is sent, so byte count will be only 6 now, from 7 to 6. And then here we will the data is sending from the slave to the master, so we will store the data here. So I2C 1 is now using MTR register, and MTR register is a register where soever data we receive from the transmission will be stored here. And this MTR register is used to store the data we receive from the transmissions, or is used to store the data that we are going to send during the transmission. But here we are receiving from the transmission I2C bus. So we will store in the MTR register from bit 0 to 7. So, and this data we get is stored in this data pointer, which is now pointing to the first will is representing that the first index of the array. It will be the data will be stored. It's indicating the first index of this array, then data pointer, and the data will be stored here. And then so it will be like that until and then the next byte will be sent, and then when the next byte is sent, the byte count will be reduced by 1 again, and then will become 5, and then the data will be received so far will be stored here. And this one in the first, when we receive the first data, it is this data will is representing that array first it will be stored in the array first index, and after that the data pointer is incrementing. It's incrementing. So in the when we receive the data for the second time, it will store in the second index. That means in the one index, that means array in the array the one index. it has 7 values, so in the one index, and when we receive another byte, it will in the next index, because when we receive this one is, I think everybody knows that when we receive a data, it will be stored in the first 0 index, and this data pointer now increment to next index. So when data is received, it will store in the that array index 1, and it will increment point to the next index again. So when data is received, it will store in the index 2, and then this data pointer is incrementing, so it will point to the next index, that is array of index 3. And so when data is received, it will point to, it will store in that index, that is in the array of index 3, and is incrementing to the next index, like that. So it will do until the byte count is less than is greater than 1. That means until the byte count is 2. When the byte count is equivalent to 1, it will come out of the loop, and we will write the conditions of byte count 1. So the condition of byte count 1 is I2C1 implies MCS equal to 5. 5 means what? Here see only this is the, in this line the most we have to focus only in this. This is the most important thing. So here it is saying I2C is just using this MCS register, and the MCS register value is equivalent to 5. And what does 5 means is 1, 2, 1. And we can write here 0 because it's hexadecimal representation, and this is 1 bit. That means execute whatever command necessary, and this one is stop bit. Here we are considering it is the condition of last byte. When this loop is greater, when this loop the byte count is equivalent to 1, it comes out because there is only 1 byte count left, and this is the condition of only 1 byte count left. That means the last byte. And so here I'm saying during bit execute whatever command necessary, and send the last byte, and then stop the transmissions. And I don't need to set the start bit here because the bus is already active, and the start bit is already set in the hardware by a previous line of code. So because of that, so we will send the last bit. So we'll say here I2C1 implies MCS equal to no I2C1 way to done. Sorry, my bad. Way to done. Way to done. What does this function do is, what does this, let me just my knee is paining as I am sitting for a long time. And then yes, this is the last conditions of sending last byte. This is the condition of sending last byte, and so we will send the last byte here. And what this condition function says is, where is that function? Yeah, this is, so here the bus is busy, that means I2C is using MCS register, and MCS register value is equivalent to 1. 1 is the busy bit, so here the bus is busy in sending the last byte, and we're checking here, okay, the error. Okay, that means I2C is now using MCS register, and MCS register value is equivalent to 0x0e. That means we are checking the error or not in sending the last byte. So this is, okay, we are checking, okay, E means 1110. That means this, okay, data acknowledgement bit, address acknowledgement bit, error again bit. Okay, we're checking the error here, so this tree will be checked, and busy bit will not be checked, as we're checking only the error, and error is usually caused by this. Error is usually caused by address acknowledgement bit or data acknowledgement bit. So we are checking only this tree, not this. Okay, so the last byte is sent as the bus is busy here, as this is busy bit, and so the bus is busy in transmitting the last byte, and we are checking the error, if there is error, or okay, that the last byte sent is acknowledged or not. If okay, the last byte sent is acknowledged, then this value will be, okay, returned. Okay, this is the value when data acknowledgement bit is, okay, acknowledged, then its value is 0. We are not checking address acknowledgement bit, as we are not sending address here, so its value, okay, will be 0, and then error, okay, will be 0 because the data acknowledgement bit is acknowledged, and we are not checking the busy bit here. So if there is no, okay, error in the transmission and the data is acknowledged, then this value will return. And if the data is not acknowledged, okay, then this data acknowledgement bit will be 1, as the data is not acknowledged, so the data acknowledgement bit will be 1. Okay, this will be 1, and we are not checking address acknowledgement bit, as we are not sending address. So, and then error will be 1, as the data is not acknowledged, and the busy bit will be 0, as we are not considering the busy bit, we are checking only the error. Okay, so if there is error in the transmission of the last byte, then this value will be returned. Okay, return. So if, okay, if error is, okay, returned, if error value is returned, it will be stored here. If no error, then those, okay, 0000, okay, value will be returned and stored here in this variable. Okay, this is just a variable. Okay, and so, sorry, my mistake. I have done one mistake here. Okay, here, okay, this address acknowledgement bit, okay, will be, not checked. That means the acknowledgement bit will not be, sent by the master to indicate that it is the last transmissions, and so the Slack will know it is the last transmission. So because of that, this is the address acknowledgement bit will not be, okay, checked. The acknowledgement bit will not be, okay, sent. Okay, acknowledge will not be sent, so this address acknowledgement bit will not be checked. Okay, since this is the last byte, sent, acknowledge will not be sent by the master, so we will not check the data acknowledgement bit. Okay, the data acknowledgement bit, so okay, we will not, okay, sorry my bad. So you know and so this is the last byte, so that the data acknowledgement bit will not be sent, so that data acknowledgement bit will not be checked, so we will not check any of this. We will not check any of this and just remain quiet. Not doing anything, just remain quiet. The snap device, we will not check any one of this. We will not check any one of this, as this one, the acknowledgement bit, will not be sent. So will not be sent. That means acknowledge will not be sent by the master device, so this data acknowledgement bit will not be checked, as this is the last byte, so we will not check this. We will just remain quiet, as we doesn't need to send acknowledge. So I don't need to write that. So here error is not returning, only we are considering the data is transmitted well and fine, so that 0000 value will be written here and will store in this variable. So we are considering there is no error. So we will just store the last byte here, and then we will say I2C1 implies MDR, because in the MDR register we are receiving that data, so we will just store that data in the array index locations. The loss that means from 0 to 6 means start from 1 to 1, so it will be 7, so like that, and then the loss, and like that, and doesn't need to increment anymore, because there is no more index, so doesn't need to write plus plus. So because of that, array index is starting from 0 to is from 0 to 7, so this will be stored in the last index. So it will be stored in the last index, 6 index of that array. This one, this index last locations, that means 6 index. I believe people will understand. And so doesn't need to increment any further. Here plus plus don't need to write, because there is no more index, that is because this is the last index, so it will not increment any further for the next data to be stored, because there is no next data. This is the last data. Because of that, and then we will finish. We will write let the transmission be finished. So I2C1 is now using MCS register, and so as well will be equivalent to 0 as 40, and 4 means 0. So this is the 6-bit 6-bit is a bus busy bit, and 6-bit says when this the bus is busy for a while, and when this bit after some time, when this bit bus busy is low, then the transmission is complete. So here it says when this bus busy bit get low, the transmission is complete. And so we will write here when this MCS bit 6, this bit 6 is getting low after the bus is busy for quite some time, the transmission is complete. So here the transmission is complete. That's the meaning of this line. And then as the transmission is complete successfully, we are considering, we will say return 0. Return 0 means no error. So in this way we are sending the data from the slave device to the master, and the master is receiving. That means the master is reading the data from the slave device, and again the data. And here again, forget everything. So this is the main functions, and so here we are just writing an array of 7 values, and this is the values are empty, and we will just call I2C initialization functions. So we will write I2C1 and then I2C1 init. Calling I2C initialization functions. Here initialization of I2C is all done, and here we will write let's do it inside the for loop, and then call that functions. What is the functions? I2C1 read, and we will pass the slave address, and the first memory location, the RAM address in the slave device. Starting the first memory location, so it will be 0x00 and 0x00. This one 0x00 is equal to 0. We can also write that. So I will just write 0. And the value of byte count I have to pass. So there is 7 byte to count, so I will write 7. And then here I have to pass that array, so that all the data is collected here. So I will say time back. So in this way data is received from the master, from the slave device to the master. And so receive means it is reading from the slave device, and the master will get it. So that's it. So we are getting data from here. Okay, and then reading first, and then second, and then third, like that up to 7, because we have that array contain only 7 index. Because of that, we are just receiving only 7 data from this RAM memory location of slab device GS1307, and it will be sent through this SDA line bit by bit, and will receive by this CORTEX M processor, that is the master device. That means the master device is reading data from the memory, RAM memory of this slab device. So in this way, the data transmission process is going on. And I forget to write one code that I usually, but this is not related to I2C. Again, I'm just writing it because the code may sometimes use float values or not. Okay, so this is not related to I2C, because just saying if the code may use float values or not, then just write this line of code. So we will write void system init void LCD. The system is using CPACR restore and its value equivalence to put into J0 F 0, because this F value is 111, and this is the coprocessor 11, this is the coprocessor 10, and this is necessary so that CORTEX coprocessor is the floating point unit of the system, because sometimes the code use the float values or double values. That's it. This is only about how if the code is saying to use the floating point unit of the system by the this is about just not related to I2C, but if the CORTEX processor need to use is using in the code those float or double values, then is using the floating point unit of the system. Okay, that's all. It's not related to I2C code. Is in every code I write this, whether I'm going to write this for any code in timer, GPIO, UART, SPI, intro, because sometimes the code use float values or double values. That's all. So in this way, data will be read from the slab device by the master by transmitting all those data bit by bit in the SDA line and synchronized with the clock line. So thank you all for this session.